Hello. In this video, we're going to look at combining transformations. So let's say we have the graph of x squared, and we want to graph y equals 2f of x minus 3. Let's describe the transformations and determine the order we should apply them. Well, in English, y equals 2f of x minus 3 would mean a vertical stretch by a factor of 2 and a vertical translation of 3 units down. In other words, we have to take those y values and multiply them by 2 and subtract 3 from them. But the thing is, let's look at a graph here first, okay? Here's our graph. Starts at the origin, over 1, up 1, over 1, up 1. Right, there's our typical parabola. If we wanted, we can add an extra point at 2 and 4, right? But yeah, there's our parabola. Over 1, up 1, over 1, up 1, over 2, up 4. And so we have this table here with the values -2, -1, 0, 1, and 2, 4, 1, 0, 1, 4. So when we talk about multiplying the y values by 2 and subtracting 3, I mean, the most logical thing to do, if we're reading it in English, multiply by 2 and subtract 3, would be to take the 4 and multiply it by 2 and then subtract 3. But we could technically subtract 3 and then multiply by 2. I mean, which order is going to be correct? Should we do the multiplication first or the subtraction first? Should we do that stretch first or the translation first? And some of you might be saying, well, it seems like we should do the multiplication first because, well, you know, bed mass, or we're reading left to right, or something like that. But let's just try both. Let's just see our two options here. So option 1, okay, option number 1, we're going to try to do times 2, then subtract 3. So the x values will remain the same, but the y values here, oh, let me call those our y values here. Our y values are going to be multiplied by 2 and then subtract 3. Okay. So 4 times 2 is 8, minus 3 will be 5. 1 times 2 is 2, minus 3 is -1. 0 times 2 is 0, minus 3 is -3. -1 and 5. Okay, so that's option 1. What about option 2? Maybe I'll put that over here. Option 2 would be, again, to keep the x values the same. But in this case, we're going to, for the y values, we're going to subtract 3 and then multiply by 2. Okay, so 4 minus 3 is 1, times 2 will be 2. 1 subtract 3 is -2 times 2, that'll be -4. These aren't looking the same as before. 0 minus 3 is -3 times 2 is -6, then -4 and 2. So if you notice, these two options are giving us very different y values. And that means that, well, the order that we're going to apply them in does matter. So it's not going to be like we could do it one way or do the other. It is going to be one option's correct and one option's incorrect because they're not the same final value. But I mean, you could make an argument for either case. And so in a situation like this, when you could argue both ways, what we do in mathematics is we just decide on a convention. We decide that because this thing is kind of ambiguous and it could mean option 1 and it could mean option 2, and option 1 and 2 are both different, all the mathematicians in the world, they get together at a conference and they just decide what it's going to mean. They pick one of the options and then they make sure they tell everybody and everybody just follows along. It's convention. So let's go on Desmos and we'll type this in and we'll see what Desmos does, because Desmos follows the conventions of mathematics. The people who program Desmos make sure that they follow the typical rules that mathematicians have all decided on in agreement. And so let's see what it looks like on Desmos. All right, so here we have the graph of x squared. And we're going to type in y equals 2f of x minus 3. Well, if we look here at the vertex is at 0 and -3. If we remember from the tables we just made, one vertex was at 0 and negative 3, and one vertex was at 0 and negative 6. So I think right away this tells us that the option that had the vertex at 0 and negative 3 is the correct option. And we can look at a few more points here. We have a point here at 1 and negative 1. And we have a point here at, let's see, not that point. We have a point at 2 and 5. So I think that's going to clue us in pretty clearly. How do we get to the point 2 and 5 when we used to have the point 2 and 4 on the original graph? Well, 4 times 2 is 8 minus 3 is 5. Whereas if we had 4 and we subtracted 3, that would only give us 1, and 1 times 2 would be 2. So based on this point here, I think it's pretty clear that Desmos is deciding to do the multiplication first and the subtraction second. That's how you get a value of 5 from 4. 4 times 2 is 8, minus 3 is 5. So we have to do the multiplication first, the subtraction last. And this is indeed the convention that mathematicians have decided on, and it's what we're going to do in our course. Whenever we have two different transformations applied vertically, we're going to do the stretch, the multiplication first. We're going to do the addition or subtraction, the translation last. So just coming back here to our example to finish off, it means that this option 2 would be incorrect. We definitely don't want to be doing this. It means option 1 is our correct option. This is how we're going to perform our transformations. All right, so let's take the graph f of x equals x squared. We're going to graph 3f x minus 1 plus 4. So again, I'm just going to try to help you out here, and then I'll encourage you to pause the video and give it a try. What the 3 here means is this is going to be the y values, and the y values are going to get multiplied by 3. And then the y values are going to get plus 4. Here, the x values, we only have one transformation to the x values, and we're going to add 1 to them. Remember, we do the opposite with the x. So first graph x squared, then apply these two transformations, and then get your new graph. All right, so we can start with our original graph. Maybe I'll do that in black here. 0, 0, over 1 up 1, over 2 up 4. So here's our original parabola. We can start with our original table. Minus 2, minus 1, 0, 1, and 2. 4, 1, 0, 1, 4. And then we're going to make a new table over here. Maybe I'll do that in green. So, well, actually, let's do the x values in blue, and let's do the y values in red. So those x values, we get to add 1 to them. So we're going to get negative 1, 0, 1, 2, and 3. For the y values, we multiply by 3 and add 4. So 4 times 3 is going to be 12 plus 4 is 16. Then 1 times 3 is 3 plus 4 is 7. 4, 7, 16. Now this won't fit very well on our current graph because we have to go all the way up to 16. But we might be able to get away with just maybe these 3 points. So if we had a bigger graph, we might try to graph all 5. Here we're just going to see if we can get those 3 points. I'll do them in green here. So we have the point at 1 and 4. And then 5, 6, 7. We've got 0 and 7. And we've got 2 and 7. So here's our new parabola. And visually, I think we can see the different transformations. We've made it a lot taller, so that's going to be the stretch by a factor of 3. We've moved it up 4. You can see clearly the vertex has moved up. And we've moved it to the right by 1. Again, we can see it moved over horizontally to the right. All right, so I'm going to give you a graph. It's just some random points here. And I would like you to graph y equals 6, f 1/3, x plus 2, subtract 5. So take these 5 points and apply all these transformations and then create a new graph. And you'll probably need a new grid just because it'll be in a different location. So go ahead and pause the video and give it a try. All right, so assuming you give this a try, let's go ahead and start with our basic points here. We're starting with the values -2, -1, 0, 1, and 3 for the x values. And the y values are 4, 5, 4, 3, and 5. Now, for our new graph, we're going to have a lot of changes here. So let's take a look. For the x values, we have to, what do we have to do to the x? Well, we have to do this thing, which is going to be multiplied by 3. We do the reciprocal. We have to do this thing, which is going to be subtract 2. For the y values, we have to do this thing, which means we multiply by 6. Then we have to do this thing, which means we subtract 5. So each one of these affects different values. The 6 and the -5, those affect the y values. The 1/3 and the 2, those affect the x values. We have to do the multiplication first, always. Then we have to do the addition or subtraction last. And the things inside the x have to be flipped around. So the 1/3 becomes a times 3, and the plus 2 becomes a subtract 2. All right, so if you messed up some of those, pause the video and see if you can adjust your table of values to make sure it's got all the correct values. All right, so let's go ahead and rock and roll. We have, for the x, -2 times 3, that'll be -6, minus 2 is -8. -1 times 3 is -3, minus 2 is -5. 0 times 3 is 0, minus 2 is -2. 3 minus 2 is 1. 3 times 3 is 9, minus 2 is 7. Okay, y values. 6 times 4 is going to be 24, that's pretty big. Minus 5 is 19. 6 times 5 is 30, minus 5 is 25. The 4 again gives another 19. 3, okay, 6 times 3 is 18, minus 5 is 13. And then the 5 is, again, 6 times 5 is 30, minus 5 is 25. So a lot of mental math going on there to go from our old table to our new table. But once we have our new table of values, we can simply put these on a graph. So let's go ahead and move down to a nice XY axis. Now again, if you had a nice grid, you could just count over on the grid. If you have a blank XY axis, don't worry overly much about scale as long as everything is labeled and sort of in the general quadrants. Shouldn't be too bad. So our first point is at -8 and +19. So let's go ahead and just kind of label this as maybe -8 and +19. So there's our first point right here. Next point's at -5 and 25. That's going to be a little bigger. So there's our second point. Our third point is at -2 and 19. So that's going to be back over here. Our third point is at 1 and 13. So our fourth point, 1 and 13. And our final point is at 7 and 25 again. So maybe over here, 7 and back to 25. Now, because the original graph didn't have any arrows, we don't add any arrows on the new graph. Because the original graph had straight lines, we connect the points in straight lines, and there's our nice, beautiful transformed graph. Now again, if you were to write the transformations, these would be a lot of words. We'd have to say vertical stretch by a factor of 6, horizontal stretch by a factor of 3, and so on. which is why, honestly, we write the transformation equation. Even though it's a little bit tricky to decipher and then to apply them all, by simply writing y equals 6f 1/3 x plus 2 minus 5, you can save a lot of space because you can communicate 4 different transformations very quickly and very efficiently. That's honestly one of the reasons we use this transformation equation. It's a very compact, very efficient way of explaining these 4 different transformations. Now I've got one last question here that's a little bit interesting. We're going to, again, focus on this graph that we have here with these points. And I'm going to give you a bit of a strange transformation equation. Y equals f 2x plus 6. Go ahead and pause the video and see if you can come up with the transformation. All right, so you might be tempted to think, oh, this means 2 times x, which means half. So we take these values and multiply them by a half, and then plus 6, so we're going to subtract 6 to the left. But if we look at Desmos, I don't actually think that's what we're going to get. All right, so here we have the original graph in red, and here we have the blue graph, which is supposed to be y equals f 2x plus 6. And I want us to focus on a few things. Now, first off, if you look, the graph does look similar. It's had some horizontal translations and stretches applied to it. It hasn't changed vertically. It's the same height vertically. And we could say, oh, this 2, yeah, it looks like it's half as big. If we look at the original red graph, it's kind of this long. And the blue graph looks about half as wide, so it's stretched by a factor of 1/2. But to move 6 left, I don't know if it's moved 6 left. In fact, if we look at a point here, for example, if you look at this point, -2 and 4, if we were to stretch that first, we would take the -2 and multiply it by a half, which would make it -1. But then if we move that 6 left, that should be at -7. If you look, that's only at -4. And I think the easiest way to see what's happening is I've labeled this point on here -3 and 4. And I also want to put that point on here, 0 and 4. This is kind of like the middle of the graph, or the y-intercept. This point here, when you stretch it, it doesn't change horizontally because it has a value of 0. So 0 times anything would be 0. And then when we look, it's only moved to the left 3. It hasn't moved 6 left. And this is really strange. What I'm going to do is actually rewrite this transformation equation for us by putting an extra set of brackets. Now, if I do that, suddenly the graph pops over there, and now we have a point over at -7 and 4. This graph is moved 6 left. But this obviously isn't the same equation that I had because I've changed it. If you multiplied it out, this would be 2x plus 12. To get back to the original graph I had, I have to put a 3 in there because 2 times 3 gives you 6. So this is the factored version of what we had. And this actually gives us a different interpretation. So this here is the correct graph, and this is the correct way of writing the transformation. And what this would read as is only 3 units to the left. So let's pop back and see what's happening. When we're given a transformation equation, f of 2x plus 6, because the 2 and the 6 aren't really set up properly, they're not factored out, we can't read this in English like we would expect. This does not mean 6 to the left because it hasn't been written in its proper form. We have to write it as f bracket 2x plus 3. Once it's been written in the proper form, well, then we can go ahead and do the transformation. The x values are going to get multiplied by a half, and then we're going to subtract 3 from them. But it's only in this proper form that we can read off what the transformation is trying to communicate. This is sort of, it's improper. It's not the right format. And formats are really important. For example, if I was talking about a date, right, I said we're going to be meeting on 03, 05, 2030. Well, I think it's pretty clear the year we're going to be meeting in 2030. But '03 and '05, I mean, does this mean January, February, March? Does this mean March 5th? Or does this mean 1, 2, 3, the third day of May? Is this May 3rd? Is this May 3rd or is this March 5th? And I mean, depending on what's happening at this meeting, it's really important to know. You don't want to miss the meeting. There could be prizes. Who knows what's happening at this secret meeting on 03, 05, 2030. So you want to show up to it, but you don't want to show up at the wrong time, right? If it's on May 3rd and you show up on March 5th or March 5th and May 3rd, this is tricky. And so whenever you're writing a date, you want to make sure that everybody understands that you're either doing day, month, year, which honestly to me makes sense. You kind of go in increasing order, right? The day is first, then the month, then the year. But some people are really in love with month, day, year. And this leads to kind of some ambiguity with dates like this. Now, I wish the whole world would standardize and just pick, day, month, year, but until we do, often forms will write down which format they're asking for. They'll give you either this or this somewhere on the form telling you, okay, please write your date in this format. I mean, there's even other formats, right? There's year, month, day. I don't think we're meeting in the third year of the fifth month of the day 2030, and there aren't 2030 days in a month, but still there's all sorts of different ways to write the day and the month and the year. And this idea here kind of relates to what we have here. It can become very chaotic if we have all these different forms for the transformation equation. So again, mathematicians have decided that you always have to use the factored form. If you're going to read a transformation, it has to be written down with everything factored out, and you have to have this double set of brackets so that this is the correct way to read it. So once it's written properly, you can see, okay, it's going to be 3 left. This form, it means nothing. It's garbage. We throw it out. We don't consider anything here. We're not allowed to read this form. We can only read the final factored form. All right, so let's go ahead and take some notes on this. So we have the transformation equation y equals a. I guess, yeah, we should write what we're doing here. We have multiple transformations. Multiple transformations. And so the general form looks like this. Y equals a, f, b, x minus h plus k. And so in this general form, we have the a, we have the b, the h, the k. A and k are going to represent y values. So a is going to be multiply y values by a. K is going to be add k to the y values. Or you could read it as a stretch by a factor of a, translation of k units up. And then for b, these are going to be x values. So for b, we're going to multiply the x values by 1 over b. And for h, we're going to add h, because we've already got the subtraction here. So that kind of has already flipped it around for us. Add h to x values. So this is the full transformation equation. It's got all of the stretches, all of the translations, the x's and the y's, and it's written in its nice factored form with the double brackets. That way you can clearly read off the transformations. So let's go ahead and do an example here. I'll go ahead and give you a graph. So we're going to have the point 3 and 1, and 6 and 3. So we're just going to have 2 points, just a nice little straight line. 3 and 1, 6 and 3, just 2 points. And we want to find the new graph. Y equals 2 plus f 3x minus 9 times 4. Now I've intentionally written it in a super messed up form, and you need to first put it in the proper form. Then you need to determine the transformations, apply them to the 2 points, and create the new graph. All right, assuming you gave that a try, the proper form here would be 4f 3x minus 3 plus 2. Then we would apply, here I could say, let me make a little bit more space. So I would apply for the x values, we're going to multiply by 1/3 and add 3. For the y values, we're going to multiply by 4 and add 2. So my original table with 3, 1, and 6, 3 is going to become, let's see, so 3 times 1/3 is 1, plus 3 is 4. 6 times 1/3 is 2, plus 3 is 5. And then for the y values, 1 times 4 is 4, plus 2 is 6. 3 times 4 is 12, plus 2 is 14. And then you would just plot those 2 points on a graph. So we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Just gets a little crazy up there. So we got 4 and 6. Let's do this in blue. 4 and 6, 5 and 14. And there's our new graph. So for practice, you can try worksheet 8 and 8.5 and maybe include one of those examples in your notes. And then any things to remember, and probably the most important thing here, well, there's 2 things. One is if you have f of 2x plus 6, this is the improper form. You have to write it as f 2x plus 3. So you have to have the proper form. And the other thing I would say is that you have to do the stretch first and the translation last. So the order that you do the transformation in matters, and mathematicians have decided that the stretches comes first and the translations come last. All right, hopefully you enjoyed this video. And as always, thanks for watching.